Have you ever wondered how one single glitch, maybe a tree branch falling on a line somewhere, can knock out power to an entire city? Well, today, we're going to dig into the surprising fragility of our power grid and the really smart tech that could actually stop a blackout before it even starts.
I mean, it's a question that's probably crossed your mind when you're sitting in the dark, right? It just feels like it shouldn't be possible. How can this one tiny failure in such a huge, complex system cause the whole thing to just shut down?
Well, the answer is a phenomenon with a pretty fitting name, a cascading failure. It's basically the grid's own high-stakes version of the domino effect. One goes down, and it starts a chain reaction that takes everyone else with it.
All right, so let's really get into what this domino effect is all about. What is it that makes our power grid so incredibly vulnerable to this kind of collapse?
To really get to the bottom of this, we first have to understand the single most important rule that keeps our lights on. It's this constant, incredibly delicate balancing act.
Everything, and I mean everything, comes down to this idea called frequency stability. You can think of it as a perfect, real-time balance between the power being made and the power being used, right across the entire network.
And this, right here, is the grid's golden rule. At every single moment, the amount of power being generated has to perfectly, exactly, match the amount of power being consumed, what the engineers call the load. It's not a suggestion. It has to be perfect, always.
And here's a fantastic way to picture it. Think of the grid's frequency as its heartbeat. Here in North America, that heartbeat's at a super steady 60 hertz. If that rhythm starts to wobble even a little bit, the entire system is in deep, deep trouble.
So what happens when that heartbeat does start to get shaky? For decades, the only solution we've had is basically a giant, clumsy emergency brake.
It's a system called under-frequency load shedding, or UFLS, and its job is, well, it's brutally simple, really. It intentionally causes blackouts in some areas to stop a much, much bigger blackout from taking down the whole system.
But here's the thing you gotta remember. UFLS only kicks in after things are already going wrong. It waits for the grid's heartbeat to drop to a dangerously low level, and only then does it flip a switch and just cut the power to a massive, pre-planned area. So yeah, you can probably see the problems here, right? This old way is reactive. It waits for the disaster. It's imprecise. It's like using an axe for a job that needs a scalpel, often cutting way more power than it needs to. And it's outdated, using fixed settings that might not be right for what the grid is doing at that exact moment.
Okay, but what if? What if we could flip that script? What if the grid could actually see a crisis coming and do something about it before that heartbeat ever started to fail?
And this is where this incredible technology, called Wide Area Measurement Systems, or WAMS, comes into play. Seriously, think of it like giving the grid a brand new nervous system. It uses all these high-speed sensors, all synced up with GPS, to get a complete, real-time picture of what's happening everywhere, all at once.
So to test this new nervous system, researchers modeled it on one of the most gigantic and complicated grids on the planet, the Western U.S. power grid, which provides power to a huge chunk of North America. They wanted to see if it could handle the real deal.
Okay, so now that the grid can see what's happening in real time, how do we use that to build a smarter, faster, and way more precise defense system for our power?
The solution is called intelligent load shedding, or ILS. And believe me, this isn't just a small upgrade on the old way of doing things. It's a total game changer. It completely rethinks how we protect the grid.
So instead of watching the symptom, that falling heartbeat, ILS uses its new nervous system to see the root cause. It looks for that immediate, massive surge of electricity on the big transmission lines that happens the very instant a power plant goes down.
This is basically the brain of the ILS system, and it's always working. It's in this constant loop. It monitors the grid, it computes the exact power deficit, and then it executes a command. And it does all of that in just milliseconds. It's incredibly fast.
So here's the real magic. ILS doesn't swing a sledgehammer. It performs a surgical strike. The second a generator fails, it detects it, instantly calculates the exact amount of power that was lost, and then cuts just enough power from exactly the right spot to rebalance the system before that heartbeat even has a chance to drop.
Now, all of this sounds amazing on paper, but does it actually work when things get really bad? Well, the simulation results are, honestly, they're pretty dramatic.
To really push this thing to its limits, the researchers simulated an absolute nightmare scenario. 2 enormous power import systems into California failing at the exact same time. We're talking a sudden loss of 2,900 megawatts. Just gone.
Okay, just look at these two graphs. On the left, that's the grid without ILS. See how the lines just fly apart? That's chaos. That's the grid's heartbeat flatlining. The whole thing collapses in under 10 seconds. But now look at the right. That's with ILS. The system takes a huge hit, you can see it dip, but the lines pull back together and stabilize. The grid stays online. It survives.
And it's not just about taking one big punch. Look at this table. This shows ILS responding to a simulated nuclear plant outage. See how it's making these tiny, precise cuts over several seconds? It's constantly making these little micro adjustments to keep the system in perfect balance. This is intelligence, not brute force.
And that really brings us to the big question, doesn't it? As everything in our world, our cars, our homes, our lives, becomes more and more electric, keeping the grid stable is absolutely critical. And smart, predictive systems like this one might just be the key to making sure the lights stay on.